Let's talk about energy. Here I have the law of conservation of energy. The change of kinetic energy plus the change of potential energy plus the change of thermal energy equals 0. And there are many forms of energy. Thus far, we've talked about translational kinetic energy, which is 1/2 mv squared. There's rotational kinetic energy, which is 1/2 I omega squared. Remember, I is the moment of inertia, omega is the angular velocity. There's the gravitational potential energy, that's just equal to mgh. Spring potential energy, which is 1/2 kl squared. Remember, the k is just the spring constant here, and the L is how much it has been stretched or compressed. And then we also calculated heat. We had two ways of doing that. We had mc delta T. You would use this when the temperature was changing, or we had plus or minus ml, and we used this when the phase was changing. Now we are introducing electrostatic potential energy, and the particular equation I want to focus on right now is K times Q1 times Q2 over R. This K here, this is Coulomb's constant, the 9 times 10 to the 9th, different from this K here, which is the spring constant, and depends on the spring. Okay, so Coulomb's constant up here. Q1 and Q2, of course, these are lowercase q's, so polarity matters for the charge. R is the distance between the centers of the two objects. If these two objects could be point charges or some kind of spherical distribution, like two balls that are charged, of course. So let's see how we would apply this electrostatic potential energy, how we would use it in conjunction with the law of conservation of energy. So down here at the bottom, you can see I have two balls, A and B, that are stacked on top of each other. And we'll just assume that A here is on the ground. So get that on the ground there. Okay, good. And they're both going to be, these are identical balls. That is, they have the same mass, they have the same radius, etc. And they also have the same charge. So they're going to repel. So this picture shows the initial setup. And then we're going to release B, and A has nowhere to go, but B is going to fly upwards. So B is going to end up flying upwards. And the question is, how high is B going to get? So if we're using the law of conservation of energy, at the beginning, well, let me first write it out here. And so to begin with, it's released from rest, so it has no kinetic energy to begin with. And then when it gets to the highest point, that's when it's going to have stopped. So that means there's no kinetic energy at the end. So there's no kinetic energy here to worry about. And there's not going to be any thermal energy for us to worry about either. So there's only potential energy. And so what we've got here is the final minus the initial. Well, initially, so that just means those two are going to be equal to each other. But initially, what I've got is only electrostatic. So we've got the initial electrostatic energy, and that's what's going to be for the initial side. And for the final, I'm going to have, let me rewrite this slightly here. There we go. Okay. So this is PE final minus PE initial equals 0. So these have to equal each other. Okay, and so initially, what do we have? We have just the electrostatic initially. And we'll assume that B, we'll just assume that where B is to begin with is 0 height. That's where I'm going to say H is 0. And so that means for the final, we're going to have the potential energy electrostatic final, plus, of course, there's going to be gravitational final. Okay, so what does that all look like? That's going to look like, actually, let me go down here. it's going to look like this. I'm going to have K. Since they both have the same charge, I'll just call it Q squared. R initial plus M G, I'm sorry, I said R initial, I mean R final. And this is the final height, which we're looking for. And then at the beginning, we have KC squared over R initial. And what I want to stress here is that even though we have two objects, two balls, and for both the initial and final, we only have one potential energy term. This is the potential energy between them. And I only write it down once for, in this case, the initial and for the final. You don't write it down twice. That would be double counting. This has all the potential energy that exists between B and A in the beginning. This has all the potential energy that exists between B and A at the end. Now, let's look at one other situation. And that's between two parallel plates, in other words, a capacitor. Now, in this case, the potential energy term takes on a very special form. It's just Q, E, D. But here, D is the distance to the attractor plate. Now, what do I mean by the attractor plate? Well, let's say that I have got a charge down here, and it's positive. The negative plate is the attractor plate for this. And so what would D be? It'd be the distance from here all the way up to here. If I had a negative charge, I'm just going to randomly put a negative charge here. Here's my negative charge right there. Okay, its attractor plate is way down here. The positive plate is the attractor plate. And so this charge, D, is going to be from here to here. That's what D is going to be. Notice, by the way, for this formula, Q is capitalized. So we're doing the charge magnitude. And that means that the potential energy, whether it's a positive charge or negative charge, it's going to have a positive potential energy. And the key thing to take note is that the potential energy is directly proportional to the charge's distance from the attractor plate. So if that distance is 0, there's no potential energy. If you double this distance, you double the potential energy. If you triple the distance, you triple the potential energy. It's directly proportional. It's a linear relationship. And that makes it easy to do, relatively easy anyway, to do an analysis such as you have to do in this problem.